After we implement the data loader and the data set, we can get the data from the file system. So that the next step is to implement the training loop. So here is the typical training loop. There's three things we need to do here. The first, we need to define the model. So we will go back to the model later. For now, we will focus on the optimizer and the loss function. So those three will be the most important component in the training loop. So we need to have a model so we can use the model to handle the data, and we need an optimizer. The optimizer is using to check the result generated by the model and compare the result with the ground truth. And then we will using the loss function to do the comparison. So after we get the loss or the error between the prediction and the ground truth, we need to propagate the loss error back to the model and modify the weights, the parameters of the models according to the gradients for each variable, for each parameters in the model. And so we have a lot of optimizer. There's a lot of optimizer has been implemented inside the PyTorch framework. The SGD, the stochastic gradient descent, is one of them. And this is the most simple one here. And for this one, for most of the optimizer, the first argument must be all the parameter list for the whole modules. So you can simply using this function, the model, which is CNN here, the CNN dot parameters. We can using this function to get the parameter in every layers of the model. So you don't need to collect the parameter by yourself. The PyTorch framework will do this for you. And the second one is the learning rate. So you need to specify the learning rate for the stochastic gradient descent optimizer. And for other optimizer, you may have extra parameters. Okay, so first of all, you need to define those three things. And of course, we have a lot of different functions available in the PyTorch framework, and you may need to write those functions by yourself in the future. But for now, we just using the built-in cross entropy loss as our loss function. Okay, and so here is the whole loop of the training. So first of all, we will read the data from the data set or data loaders, and feed this data into the models. So we will execute the feed forward the forward path of the function of the models to produce the predictions, and those predictions will be fed into the loss function, and the loss function will compare the prediction with the label or ground truth of the data set. So, and it will generate a loss, and the loss will be fed into the optimizer, and the optimizer will use those will do the backpropagation path and to calculate the gradients of every parameters in the models. So the value of the cross entropy loss will be propagated to every parameters in the model, and we were using the gradient to do a small step to modify the the parameters, the value of parameters by using the learning rate. So learning rate, typically learning rate will be a very small value. So for each time, we just update the parameters a little bit, so that we will guarantee that it will update. It will this update will decrease the value of the loss. So we will go through this this loop, for all the data in the data set. So for each time, we will get a batch of a sample from data set, calculate the value, and calculate the loss function, and calculate the gradient for each parameters, and using those gradient to update the parameters of the models. Okay, so here is the real implementation of the above picture. So the first loop will be the epoch. So for each time of training, we might check every samples in the data set for a couple of times. So this will be defined as the epoch parameters here. So typically this parameter will be acquired from the command line, or you can hardcode it as your deep learning program. And we need to call the CNN.train function. This is really important. Since there is some modules inside a deep learning program will work differently when we are in the training mode or in the evaluation mode. So that we need to call the model.train functions before we do anything in the training loop. So after we make a model, enter the training mode, we can using the loader to get a mini bench of the data. So for this line, we'll get the data in the batch X and batch Y, which is the label of the data, and the batch X is the sample image itself. And then we can using the variable function to convert those into the parameters for the deep learning framework. So the BSBY, so after we convert it into the variable, we can feed this variable into the CNN to execute the model. So this is very important, since if you cannot send the tensor to the CNN directly, you need to convert it into a variable. Okay, and after we feed it into the models, it will produce an output, and we get the first output, and which is the output of the system. Okay, and after we get the output, we can feed the output and the by, which is the ground truth of the samples, to the loss function. So the loss function will take two inputs. The first one is the prediction from the model. The second one is the ground truth. Okay, so after those function get those input, it will compare them and produce a loss, which indicate the difference between the prediction and the ground truth. And then next step, we will, okay, let me do it. So we get a batch of samples, and we get using model to get a prediction for all samples, and then we calculate the error between the prediction and the ground truth. Then we calculate the gradients of all parameters against the loss functions here. Okay, and then we using those functions. So the load start backward will actually do the backpropagation itself. So you may wonder why the backward function does not take the model as its input. No, since we need to update the model by using the loss function, and the backward function will actually calculate the parameters of the gradients of every parameters in the system. So since this function will modify the model, in principle we need to take a model as an input, but the since that in the optimizer we have actually put all the parameters into the optimizer. So optimizer has no all the parameters here, so it doesn't really need to put the extra model the model instance in here. Okay. Okay, so after we calculate the loss function, and we can call the step function here. The step function will update the model by using the gradient calculated in the previous state. So that till now, after this statement, the parameters inside the model has been modified by using the optimizer. And in the optimizer, we have specified the learning rate, so you will modify the parameters, the value of parameters a little bit according to the loss function. And then we will go back here to get the next batch of the data and do the same thing again until we iterate through the entire data set. So after this, we will go to the next epoch to do the job. And of course, before we start the next epoch, we may do some evaluation to evaluate the performance after we check the entire database. Okay, so there's one more thing here I need to mention. In sometimes, because the memory is not enough, so we need to decrease the batch size to reduce the GPU memory usage. So in here, that is a very simple way to implement the mini batch. So we need to call the zero grade functions to reset the gradients of the models before every batch, mini batch. For example, in this example here, we will do 2 backward before we call the step function here. So when the step is in the first batch of the mini of the data, we clear the gradient, and then we call loss function to accumulate the gradients for this batch of the data. For example, the size of the batch size is 16. Okay, so in the first 16 image data, we will calculate the gradient and store it in the backward in the parameters. Then, since that's the first step, so we will not call the step here. And for the next 16 data, okay, you will call the backward again, and then you will hold state function. So since inside the backward function, when we calculate the gradient, you will actually accumulate the gradient for the new 16 images inside parameters. So totally, for each parameters, you will have a gradient for all the 16 of all the 32 parameters, the 16 in the first batch and the 16 in the second batch. So total you will have the gradient data for the complete 32 batches, 32 images, and then we will using the state function to update the parameters according to the entire 32 images. So in this way, we can increase the batch size, but only using half of the GPU memory to store those gradient data. So for example, if you have only 8 GB of the GPU memory, but you want to increase the batch size to get the better performance, but you don't have enough GPU memory. In this case, you can consider to implement in this way to decrease the required GPU memory, but you still can get the bigger base size for better performance. So after each epoch, typically we will do some evaluation to check the performance after this epoch. So for the evaluation, you need to call the eval before you do the evaluation. That's exactly the same as we talked about the training loop before. So since some of the modules, some of the deep learning building blocks, such as the dropout, it will work differently in the training phase and the evaluation phase. So we need to call the eval function before we do the evaluation, so that it will generate the correct result. Okay, so this is the same as the training loop. We get a batch of test data from the test set, and we go through the models and get the test result. But in this time, we will not using those function. We are using the function to produce the predictions. So in here, we just get the maximum value of the test output. So because the test output will be a rate of probability for each class. So we just take the one with the highest probability to be our prediction, and then we convert this data into a NumPy. This is really important because when we do the calculations, it must be, sometimes we hope that it is in NumPy, so we can use the NumPy function to handle the data. So we just convert it into a NumPy here. Of course, you can still implement this in the PyTorch framework if you want to do that, but the implementation will be a little bit different. In this case, we using a NumPy to do the calculation. So after we get the output here, so this will be the prediction. So we just compare the prediction to the label, to the test table. In here we convert it into a NumPy as well. Okay, so we just compare the value between them. So in this case, if they are equal, it will be true. If they are false, if they are not equal, it will be false. And then it will become an array of the data of data whose element is either true or false. It indicates the prediction is correct or not. And then we convert this Boolean array into an integer. So in this case, if the prediction is true, it will become 1. And if it's false, it will become 0. So it will become an array of 1 and 0. And then we sum the array together. So since the element of an array is either 1 or 0, so the summation of them will indicate the number of the correct answer. So this value will be the correct answer, correct samples here. And then we just divide the correct sample over the number of samples in the test data set to get the accuracy here. So that's the way the typical way we calculate the accuracy of the system. Of course, now those evaluation we have a number of ways to do the same thing. This is just one of the example. You can use in your way to get to calculate the accuracy of the model. And after we get the accuracy, typically we will print the epoch number. So we need to, this is the first epoch or second epoch, and then we will print the value of loss function. So we can see the loss it will be decreased according in the training procedure for each epoch. And then we print out the accuracy so that we can see that the accuracy is decreased according to the data. And the loss function is actually loss function of the training data. So if you see the loss is continue decrease but accuracy is not decreased, it means that the training has been overfit. So we can just stop it earlier, and because if the model is overfit to the training set, it doesn't help. Sometimes it will not only it will not be able to increase the accuracy of the test set. It actually will lower the accuracy of test set since the model has been overfit to the training set, and the distribution of training set, distribution of test set may be a little bit different. So in this case, we need to do the early stop. We will go back to those training strategy later in this course. But for now, you just need to know, okay, we can do the evaluation to see the loss data and see the accuracy. Of course, you can print other data as well. For example, you can print the data for the loss of the test set. So I did not really calculate the loss of data set here, but you can calculate the call the loss function to calculate the loss of the data set or the test data set, and the print is here to compare with the loss functions. So you can see, okay, if a loss function of a training set decrease, but the test for the data set is stay still or even get worse, increase. So in this case, it means that we should not continue to train it because it doesn't help the accuracy of the model at all. Okay, so we have discussed the training loop. We know how to call the loss function and how to call the optimizer to do the job, and we know how to train the model. We know how to evaluate the model, but what's the model itself? Okay, so no matter what the model is, the data precision and training loop are almost the same. So the good news is that you only need to write the one training and evaluation loop, and then you can change the model to a lot of different things to try the different algorithm, try the different architecture to select the one with the best performance in the deep learning program or in your exercise. Okay, so for the training loop, the model is a black box. It doesn't really need to change the training rule according to the model itself. So, but if you want to know what's the model, here is an example of the models. So we have the netcast which is derived from the touch.nn module, which this will be the base function for the model. Okay. So after we get the net here, in the net function, typically we only need to implement two functions. First is the constructor, the init function here, and the second one is the forward function. Okay, so inside the constructors, you need to construct the parameters for your models. So this is really important. You need to do this inside the constructor because the PyTorch framework will capture the parameter you create inside the constructor functions, and so that it will return all the parameters when we call the parameters function we mentioned before, to return all the parameters of the framework, so that you can see that this is really automatically. So we have no function called add parameters, something like that, to tell the frameworks we have created some parameters for those models. So everything you create inside the constructor will be recorded by the framework. So for example here, we set the function self.w equal to this things. So this is really important, that after you create the parameters, you need to store it inside some variable, some property of the models, directly or indirectly. Okay, so for here we store it directly. So when we store those parameters into the W here, this is exactly the place that PyTorch will record the parameters. So it's very important that you do this assignment here. And after you assign those parameters, actually in the forward function, it will, using all the parameters you created in the instructor, to assemble all the parameters together to implement the model itself. For example, in here, we just modify the W to the input data, and do the addition operation to the B here, another set of the parameters here. And this looks like an mathematical expressions, but actually it is used to construct a computational graph. So we will introduce the computation graph concept of computation graph later when we introduce the D0 framework, when we discuss the computational graph and the backpropagation and everything for the training. Okay, so when we introduce those things, we will introduce the computational graph in detail. But for now, you only need to know that the function, the expression here, is not a real calculation, since all the W input and the B is not a number, it's actually a parameters. So when we write this expressions, it will not evaluate the value. It will produce a computational graph like this. Actually, the compose a computational graph like this, and this computational graph will be a representation of this expression. So you can see that for this case, we have a two term for the addition here. So first one is C of B. The second one is this term. And the this term is actually produced by this operation multiplication here. And for the multiplication, it has two input, the self W and the input. So that we will construct a computational graph for this. So next time we will need to calculate the model for certain input. We just call this graph to do the calculation, and this graph will actually be converted into a CUDA program and send it to the GPU for the calculation. Okay, so this is no matter how complex the model is, the class function is very similar. It has two functions. One is the constructor, the other is forward function. Okay, so the previous example is a linear layer. It's an implementation of a linear layer, and for the CNN models, typically you will look like this one. So we still have a CNN class here, and which is derived from the NN modules. And we have a constructor, we have forward. So no matter what the model is, and the structure will be the same, but this time it will be much complex than the linear layer in the previous example. So in here, we using a new syntax called NN sequential. NN sequential. The NN sequential, it has no any functions mathematically, so it will not involve in the execution of a model. But you only group a couple of the operation together and make it a unit which is easier to be understood by the users. For example, here we using the NN sequential to assemble the 2D convolution, activation, rule activation function, and the master pooling to be a single building block for the deep learning framework, and we call it conf1. So it means that this is the second basic conf blocks, and we have the other conf v2, conf2, the block here. So they are very similar, but with the different the parameters here. So in today's deep learning framework, we will not actually we don't really need to NN sequential here. We can just put all the everything in an entire list, but it will be more difficult to understand by the user, especially when we print the structure of the models. So if we input in this way, when we print the structure of models, we can see that okay, the conf1 is this, the conf2 is this, so that you can give it a better name comparing to the conf1, conf2 here. So we can use in the layer 1, layer 2, or anything here. And actually, this one can be cascade. So inside the sequential, we can have another the sequential here to be to make this model as a tree. So that we need, when we write our models, we need to using the NN sequential to organize all the blocks, so that it will be easier to understand by yourself or by others. That's really important for others to know how you implement your deep learning network. So in here we have two convolution layer and we have a linear layer. So in the forward function, it's the same. We just assemble all of those components together. So we send the input into the first convolution, the convolution block, and produce an error, and send the error to the second convolution, and send the output. So we flatten the output here, and then so that we can send it into the linear layer here. But there's one important thing here. We need to make sure that the output of one block, when we're using the output of the first block here to fit it into the second block, we need to make sure that the dimension is and the resolution is compatible. For example, the output of first block should be compatible as the spec of input of the block here. For example, in this example, the output of a first block, the number of channels is 16 here, and the rule and the mesh pool, it will not affect the channel. So the output is 16. So that the input of the comp v2, which is the first block, first modules in the comp 2, which is the comp 2D here. So he must be 16 here. So if this is something other, for example, this is 32, and there's a 16, the output of first building block has a 16 channel, but the input of second block will be 32. Those two, if those two are not matched, the program here will the PyTorch will report an shift error when this for function is executed. So this is really important to make sure that the shape of those two are matched. So it actually is not only the channels. Sometimes the resolution need to match as well. But for the convolution, since it doesn't really care the resolutions, so you can see that we have no 14 here. But if this one for the output of V2 to this one, this is really important data. For example, in here, the output of comp V2 is 32 channel of the 7x7 image. So the total size is 32 multiply 7 multiply 7. So the size of the linear must be exactly the same here. So in here, for the output of the comp V2 is 32 by 7 by 7, and so that when we using the view function to change its shape to one dimensional, it means that it has 32 multiply 7 multiply 7 elements. So the size of a linear here must be exactly the same. If that's different, the system will report error. So the linear here is the input is 32 multiply 7 multiply 7, and the output is 10. Okay, so for some time, since we may have multiple linear there, so you must be make sure that the output of the first linear match the input of the second linear. Okay, so we can fit 28 by 28 for the NIST. Will fit this data into these functions, and it will for this one, you will produce the 16 5x5. The 16, it will using the 16 5x5 kernel here, since the kernel size is 5. So you will using 16 5x5 CNN filter to filter the input image. And then we will using the rerule and the mask pooling here to handle the function. So the rerule is just an activation function, which is used to add some nonlinearity into the model. Okay, so after the activation function, we will send the data through the pooling function to reduce the resolution. The kernel size is 2, so it means that you will using 2x2 filters to filter the 28 to 28 into the 14 by 14. So after this block, you will become a 14 by 14 image, which has a 16 channel, since we're using 16 CNN filters here. And then we're using another I'm sorry, this should be 32 here. We're using another 32 5x5 the filters, and so go through the redo and the mask pooling function, and then so in here we get a 32 7x7 the image here, or the feature space features here, and then we flatten it by using the view function. So finally, we're using the linear layer to convert the 32 by 7 by 7 element into 10 output, which is the prediction, the probability of the 10 classes, the 0 to 9. Okay, so that's a very simple function which we're using to implement the NIST here. And actually, you can use in a very similar way to implement any classification task. So in the second exercise, we will implement a Chinese recognition model, Chinese handwriting recognition model. So in this data set, there's more than 100,000 samples inside this data set. Each of them will be one of the Chinese graphs written by hand, written by a couple of the peoples. So for each actually in this data set, there's about 5,000 different characters in Chinese characters. So you don't really need to understand how what's the Chinese the look and feel of the Chinese character. You only need to know that those pictures are the same thing. Okay, so check the release the notebook and try to implement a model for the Chinese recognition of the program. Yeah, actually, it will be very there's nothing different compared to the NIST. The only thing is that there's more characters. In the NIST, you only have 9 digits, but in the Chinese, we have 5,000 characters, and so that the problem will be more tough. So it means that you need to use bigger, more complex models for this job. Okay, so in this exercise, the baseline is that your accuracy must be higher than 16. So if you have 16, you will got some basic scores, and you can form a team with two to four numbers, and we will have a competition for this in 6 weeks, or 6 to 8 weeks, so that we'll do a competition in the classroom, So if you we and we will we so we will uh, give you extra credit according to the score, or so or according to the rank of your performance in the competition. Okay, so there's a formula here, and in this competition you will get a different score. Okay, so and against our private test set. So okay, so that's the introduction about how to write the uh, very basic deep learning framework problem for the classification task.